Well, without further ado, we will bring in our good old friend Luis Quintanilla. Hey, Luis, how are you doing?
Hey folks, doing all right. Excited to be here.
Hey, great. So I'm going to bring your add you to stream here, and whenever you're ready to rock and roll, you go for it, sir.
Awesome. Let's do it. Thanks. All right. Well, welcome everyone. Good morning, good afternoon, good evening, wherever you're tuning in from. My name is Luis, and I'm a program manager here at Microsoft, working in the machine learning and AI space. And today I'm here to talk to you about announcing ML.NET 2.0 and some of the new stuff that we've introduced with this version, as well as talk to you about what's next for ML.NET. So without further ado, let's get started here. So just kind of move my slides here. So if you've never heard of ML.NET, it's an open source cross-platform ML framework for .NET. It's built for .NET developers, so it allows you to stay in the .NET ecosystem so you can reuse your C# and your F# skills to sort of build these machine learning models and integrate them into your .NET applications. Now, to get started, you don't need data science and machine learning experience. We have tools and different components, some of which I'll talk about today, that make it easy for you to get started. And because you're building on the .NET stack, it makes it relatively easy to go from sort of that experimentation process of trying out your machine learning models and then bringing them to production inside of your client, web apps, any type of .NET application that you'd like. All right. So with that out of the way, let's talk about what's new in ML.NET. So this past year, one of the things that we've been focusing on has been deep learning, right? And improving support for it inside of ML.NET. Now, a few months back in June, we talked about the text classification API, and we introduced it in preview. So what is the text classification API? At a high level, it's basically just a wrapper or this API that allows you to solve text classification problems using some of the latest techniques from the industry, right? So these are transformer-based neural network architectures to, again, specifically in this case, for the task of text classification. So how have we done that? Basically, we took a torch-up implementation. We collaborated with Microsoft Research to implement NASBERT, which is a variant of the BERT model. And we've implemented that in TorchSharp, right? We've then taken that model and that implementation and added it inside of ML.NET and exposed it as text classification API. Right? So what you're able to do now is you're able to take this pre-trained model, you're able to bring your data, and then using the text classification API, you can fine-tune the model so that it fits specifically to your needs and to your particular use cases, right? So again, over the past few months, since around June, we've been iterating on this, and we've been sort of trying to make the API a little bit more robust. And one of the things that I'm excited to talk to you about is that text classification is now a new scenario inside of Model Builder. So let's take a look at what that looks like inside of Visual Studio here. So if you're familiar with Model Builder, it's this extension that provides a really nice UI for training machine learning models. So in this case, I have a set of C# projects here. If I were to right-click, add machine learning, it would bring me to, it would tell me to create a sort of an mbconfig file. In this case, because I already have one created, I'm not going to go through the process, but if you had to create a new one, you would just select this machine learning model, provide a name for it, and you would get this mbconfig file here. So what that's going to do then, it's going to launch Model Builder here. You can see that if you are used to using Model Builder, this may look a little bit different, but we've organized our layout depending on sort of the data types or what the types of problems that you're trying to solve. So for example, for tabular data, this tends to be structured data, right? To solve these types of problems like classification, recommendation, and forecasting. You can find it here in the section. Computer vision, we have these here, but the one that we're going to talk about here is text classification. So to get started, you just choose text classification as your scenario. You then choose what do you want to train this on. So you can choose from either CPU or GPU. We highly recommend training on GPU. These sorts of deep learning tasks tend to run faster on these GPUs. So we highly recommend that you use that. When you go to the next step to the data, you select your data. In this case, we have this sort of freeform text comments, which is going to be our inputs. And then the thing that we're trying to predict is the sentiment. In this case, 1 is positive and 0 is negative. When we're ready to train, we just move to the train step. In this case, I already trained the model. but you can, just say train. And you can see here that it took about 40 seconds for this one model to train for me with an accuracy of about 73%. And in addition to that, it generated some code for me. So with Model Builder, code for consumption, when you want to use the model to make predictions, is provided for you, as well as if you want to retrain the model. If we take a look here, we provide you with the pipeline. So what exactly does the code for the text classification API look like? Aside from these sort of data transformations that you have to perform on your label column here, the column that you're trying to predict, it's just one line of code. You tell it, here's the thing that I'm trying to predict, and here's going to be my input, which is that free-form text. Right? And that's it. That's all there is to it. And then in terms of the consumption, you're going to use the same patterns that you may already be used to inside of ML.NET. I'm going to go here, for example. You're going to create an instance of your model input. In this case, crust is not good. Right? You're going to use predict, which is code that we provide for you, which is a really nice wrapper that just creates a prediction engine and uses it to make predictions on your data. Right? And yeah, so I encourage you to give it a try. That's basically the text classification scenario inside of Model Builder. So download the latest version and try it out and give us feedback. Now, one of the nice things about these NASPER architectures and these NASPER models is that you can kind of repurpose them for other tasks. So I just showed you what the NASPER model looked like for text classification. What if I wanted to do something else? In ML.NET 2.0, we've introduced the sentence similarity API, which is also based on that same NASPER architecture. The difference is, instead of trying to predict a category, it tries to determine how similar two phrases or two pieces of text are. If you look at this code sample here that I'm showing, you can see, for example, that I have some data here. I'm trying to compare the phrase ML.NET just released to these two sentences here. There's a new version of ML.NET, and the rain in Spain stays in the plain. So these are going to be my inputs, the things that I'm trying to determine what the similarity between them is. And then the thing that I want my model to do is determine the similarity. Now, this could be a numerical scale of your choosing. In this case, I just chose 5 as being most similar and 1 being most dissimilar. Right? From that point, you basically just go through the same process that you would with ML.NET. So you load your data into an iData view. You create a pipeline. In this case, this is all that's needed. Sentence similarity, you tell it, here's one of my sentences, here's the column for my other sentence, and the thing that I'm trying to predict here is my similarity, similarity measure. And at that point, you just fit the model, train it. For prediction, same thing, transform, prediction engine, all the things that you're already used to doing inside of ML.NET. You can now apply those same sort of patterns to this new sentence similarity API. Now, in order to make some of these sort of deep learning scenarios capable, we needed a way to pre-process data, right? So computers don't really understand free-form text. So you need some way to get that free-form text into a representation, a numerical representation that the models and these algorithms can understand, right? Now, in .NET, there's a lot of really nice solutions. So for example, if you look at BERT tokenizers, it's a really nice package from one of the members of the community, right? Nikolai, I definitely encourage you to check it out. But in ML.NET, we went ahead and we essentially created a set of APIs for this tokenization purpose, right? And one of the things that we've done is we have exposed these tokenizers and these APIs through the Microsoft ML tokenizers NuGet package. So in addition to using the English Roberta tokenizer inside of the text classification and sentence similarity sort of APIs, there's also the opportunity for you to bring vocabularies from other models, right? So for example, if you had you wanted to use the GPT-2 model, you could import the vocabulary files and use this Microsoft ML tokenizers package for performing that tokenization and pre-processing. One of the other things that this ML tokenizers allows you to do is training, right? So you can use the default vocabularies out of the box, and that works just fine. That's sort of the importing component. But the training component is, what if you wanted to expand or extend the vocabulary that's provided, right? So with this training, you essentially get to provide your own sort of custom set of words and vocabularies to be pre-processed using these different tokenization techniques. If we take a quick look here at more or less what this API looks like, in the left-hand side here, I have a sample which uses vocabulary assets from the GPT-2 model. Essentially, you go ahead and create a tokenizer. In this case, you tell it that you want to use the by-pairing coding algorithm. You provide the vocabulary assets, additional configurations here. Here's your input. And then you can just call encode on that, which will, again, take that raw form representation and convert it into a numerical format. And that numerical format might look like something like this. So in this case, the IDs are just sort of key value pairs that map individual words to sort of an index, right? And then the offset, which is where each of these tokens, for example, in D, it starts at index 0 and it ends at index 3, right? So where's the beginning and the end of these tokens, right? If you were to call the code, it basically takes this numerical representation and brings it back into sort of the raw freeform text, right? So essentially, you can use this to both encode and decode information and get it ready for these sort of type transformer-based models to make use of your data. Okay, so what is automated? So let's talk about automated machine learning. So first, let's talk about what is automated machine learning. At a high level, automated machine learning automates the process of applying machine learning models, applying machine learning to your data. Right, so you just give it a data set, and basically AutoML, what it does is it iterates over different data, whether that's the different data transformations, different algorithms, and it tries to optimize the hyperparameters in order to select the best model for your data. Right. So why? So trying to train a machine learning model is a repetitive process. It's very experimental, and there's a few steps that are involved that you typically have to go back and forth on. Right. So on the left-hand side here, we see sort of at a high level the typical machine learning process, which involves defining a problem that you're trying to solve, collecting data. You go ahead and pre-process that data, you train the model and evaluate that model. You're going to see here that these boxes that are colored in orange, the pre-process data, train model, and evaluate, AutoML can help with that, right? And AutoML can do so in not just automating it, right, through brute force, but there are some algorithms that help you optimize some of the hyperparameters that are able to allow you to sort of choose the best model for your particular problem and for your data set, right? So in ML.NET 2.0, there's a few things that we've introduced based on some of the latest from Microsoft research, a lot of the components and techniques which are found in the FLAML library, right? One of the things that we provide in ML.NET 2.0 is this featureizer, which one of the things that it does is depending on your data, it will try to recommend what pre-processing step needs to be applied to it. Right? We've also provided a set of pre-configured AutoML pipelines for the following tasks, whether it's binary, multi-class classification, or regression. We configured a set of defaults, so it makes it easy for you to get started through these code-first experiences. Right? If you're a more experienced user and you need additional customizations, you can basically do several things. One is you have the ability to exclude trainers during training process, whether maybe you found that certain trainers don't work as well as you would expect them or give you the results you need. Maybe they take too many resources. Whatever the reason may be, you're able to define that and set the different tuners and trainers that you want to use for your training process. You can define and create your own search spaces, right? So this is the list of options that AutoML is going to look for potential candidates when it's trying to optimize your hyperparameters for your models. You're also able to choose how AutoML goes through the process of optimizing those hyperparameters and searching through the hyperparameters in the search space by choosing which tuner algorithm you want to use, right? That's sort of the intelligence behind it. Instead of doing sort of brute force approach to the automation, these tuner algorithms are optimization techniques that help you do that. And then last but not least, if you want to go ahead and create your own trial runner, you're able to do that so that you can have full control over how each AutoML sort of step and each AutoML run takes place. Some other things that you're able to do, you're able to persist the trials, right? So for example, let's say that by default, AutoML just gives you the best model that it's found, right? However, there are ways that you can persist the trials, right, which are the individual runs during an AutoML experiment. So that, let's say, you wanted to save the best 5 models, or you wanted to refine how you go about choosing the best model, you're able to do that, and you're able to sort of persist and keep all the trials that took place during a particular AutoML run. And last but not least, one of these things that you're able to do is you're also able to set checkpoints. So if for whatever reason you stop early, or there's an error and your program crashes, right? When you set a checkpoint, the results at that place in time basically allow you are dumped to a directory that you specify. Right? And there's a few more things, but these are some of the main highlights here for AutoML. So let's take a look at what AutoML looks like. So I'm going to start with this quick start here and basically show you what a training or AutoML training pipeline would look like. So we start off with this column inference, which basically uses this infer columns method here. So what infer columns does is it takes a look at your data, loads a few of the rows, and then it tries to infer or guess what the data type of those rows is. All right. So if I were to run this here, I'll kind of show you what that looks like. A second here for the breakpoint to hit. So if I were to step over that, it might be a little difficult to see here, but let me just zoom in just a little bit. So if I were to inspect this item here and we take a look at the column information, we can see that there are two categorical columns. This is for the taxi fare train data set. Those columns are sort of the vendor ID, payment type. We can see that there are a few numerical columns as well: rate code, passenger count, trip distance, those sorts of things. Right? The nice things about this infer columns is that you can then use it downstream for doing other things, such as actually creating a text loader, which is what actually loads your data. Right? The other place where this column inference information can be used is in this pipeline here. Right? So when you set up a pipeline. So when you set up a pipeline, one of the things that you can do is you can use the featureizer, which I mentioned earlier. And if you recall, the featureizer, what it allows you to do is it recommends, based on what your data types are, the types of transformations that are supposed to take place. The resulting output of this is a single vector column, which is what the algorithms expect during the training process. Now, in this case, because one of the goals that or the task is to predict the fare amount, I'm using the regression sort of pre-configure set of pipelines here, and all I need to do at that point is tell it, here is the label column, and it's going to use information from the featureizer to then sort of infer the rest and just kick off a training process for a regression. Right. Now, then we get to this experiment step, and an AutoML experiment is just a collection of runs, right? So AutoML will iterate over different algorithms, different hyperparameters in order to find the optimal one. So an experiment is just a collection of those runs. Okay, so you initialize one, you configure the experiment. In this case, we're telling it these are the steps, or these are the pipeline. This is the pipeline that I want you to run. Here's the metric that I'm optimizing for, in this case, R squared. Here's how long I want you to train for. And here's a validation set that I want you to measure the performance of this model against. Right? Now, one of the easiest ways to sort of get started with this is you can or to log information is by using this log, defining the log event and just outputting to the console. And then once you run your experiment here, it's going to run for 30 seconds, try to find the best hyperparameters, best algorithm for your regression problem. And then the result is going to be a model here. Okay. So if I kind of just let that run and kind of show that here. There it is, right? So there's that logger. Now, one of the things that you're going to notice is that it doesn't actually look nice, right? Like this is just a raw sort of dump of what's happening throughout the training process. Let me kind of pull up the advanced scenario here and show you different ways that you can sort of customize ML.NET from AutoML for those more advanced scenarios. So one of the things that you're able to do is you're able to define your own monitor, right? So you can see here that there's a few lifecycle events. So for example, whenever there's a completed trial, there are things you can customize the output of that. And one of the other things that you're able to do is, as the trial completes, you're also able to persist that, right? So in this case, it's just a list of trial results. And every time that one completes, I'm saving that to the collection so that I can use it later downstream. You can see that a lot of this kind of looks the same. I'm using the featureizer, I'm using regression, but you'll notice here that here, LightGBM is one of the algorithms that I don't want to train with, right? So this is how you would go about excluding the LightGBM trainer from being used in this particular training run. Other things that you're able to do is, because these the column information here are just standard .NET collection types, let's say, for example, that I got it wrong, that rate code is not a numerical sort of column, but instead it's a categorical column, right? I'm able to sort of customize that. Other things that I sort of mentioned, right? You can set your tuner, set your own monitor, set these checkpoints. And then here, as I kind of showed earlier, right? Like you can actually get access to those completed trials and use them downstream. So whether that's saving them to a database, whatever it is that you want to do, right? You have full access to that. Okay, so let me kind of jump back to the slides here for a second. Cool. So more robust APIs for AutoML mean that in our tooling, we can bring more advanced options to you. So these are just a few screenshots. On the left-hand side is we introduced a new capability inside of Model Builder, which provides you to define some customizations in the advanced training options. So again, on the left-hand side here is if there are some algorithms that you know just don't really work for your data set, you can just choose to exclude them, right? And this is going to depend on the task that you're doing, regression, multi-class, whatever the scenario is. And likewise, you may want to choose which is the metric that I want to optimize for. So on the right-hand side here, you can see that this is a menu where you can choose the metric that you're optimizing for. So that's available in the latest version of Model Builder. Also, something else that I'll sort of mention here is that Model Builder and the ML.NET CLI run on ARM. So a few months ago, I think it was mentioned that VS, Visual Studio, can run on ARM. And as a result of that, so can Model Builder. There are a few limitations, but if you want to get your Windows Dev Kit or any other sort of Windows ARM device, please feel free to try it out and let us know. Give us feedback. And then the CLI, because it targets .NET 6, we sort of automatically, for the most part, get some of that ARM support out of the box. So yeah, check it out. So that kind of wraps up what's new for ML.NET. Let's talk a little bit about what's next. So part of what's next is more deep learning, right? So we want to enable more of these scenarios using these transformer-based architectures. One of those scenarios that I'll call out is named entity recognition. So in this case, I'm kind of showing what named entity recognition is. I'm saying, hi, my name is Luis, and I like F#. Now, depending on how your model is trained, it's able to detect entities from within text phrases, right? In this case, it knows that Luis is a person. It could easily find organizations. It could find other types of entities, depending, again, on the data set that you use and how you train your model. So how exactly have we done that? Basically, again, using the same set of transformer-based, NASPER transformer-based architectures and models. On the left-hand side here, you'll see that this is basically a definition for the NER model. And one of the things that I'll sort of call out here is that this is very preliminary, right? Like it's something we're going to introduce in the next few months. So, we're still working through this. But essentially, what you see here is just a definition of the model. It's just defining the different layers for what this particular model or this particular architecture is going to have for NER. And then it's also defining this sort of forward method here, which, if you're familiar with PyTorch, that's basically how this is applied, right? And how data gets forwarded and passed through the network. In terms of training, it's pretty straightforward. Again, if you're used to PyTorch, this is going to look very familiar. So we define a trainer. This is just kind of like a helper function here. We go and iterate through each of the batches, and then we perform a training step. Now, this training step, again, this is going to look very familiar for some folks. It does some training, does some grading setting. It does the forward pass on that, and then it sort of sets some state about the model. Inferencing works very much the same way. You iterate through each of the batches, you perform an inferencing step by doing a forward pass on the data, and that's how you're able to make predictions, right? And one of the things that I want to highlight here is this is all in .NET, right? There's no Python, it's all in .NET. Question answering kind of works the same way. We want to introduce a question answering scenario as well, powered by the NASVERS sort of architecture. And question answering basically means, given a context like the quick brown fox jumped over the lazy dog, what color is the fox? It would respond, the model will respond with brown. Right? Let's actually see that in action. So let me pull up the question answering one. And it's going to take a couple seconds to load here because I'm sort of booting from scratch here. But whenever it's loaded, it's going to basically ask me for a prompt. Again, this is for the question answering scenario. Just give it a few seconds here. Probably should have run that before. Okay, there we go. So basically, it's asking me for a prompt. So in this case, I will say we are talking about ml.net at .NET Conf. So that's the prompt. And then what's the question? What were we talking about? You can see here that it provided a list of answers, such as ml.net, ml.net at .NET Conf, and talking about ml.net, right? Which sounds right. In the interest of time, I won't do the NER one, but out of this, go back to the slides and sort of keep going. Object detection is another scenario that we're looking to introduce with the next version of ml.net. So again, it works very much the same with these transformer-based architectures. The code looks for the most part the same. So we're really excited to introduce, be introducing in the next few months object detection into ml.net. And again, the plan is for it to look similar to what the text specification similarity, sentence similarity APIs look like today, right? Providing a high level abstraction on top of Torchart. Whoops, sorry. So what else is next? Again, we want to keep working on these deep learning scenarios. One of the things that we want to focus on is accelerating them. So there's two components to this, right? One component is on the software side, we want to improve the batch support that iDataView gives you. So, so that you can actually, process data in batches, which is typically how these deep learning models process data. And then the other one is at the hardware level, right? So if you have specialized hardware like GPUs, we want to make sure that you can make the most out of it, right? And one way that we can do that is by making it easier to support accelerators, such as those that the Onyx execution providers let you tap into, right? And we want to continue to drive making it easier to consume Onyx models inside of ml.net. We know that sometimes that process can be a little bit confusing. So if there's any guidance that we can provide and any help we can provide for you folks, that would be ideal. LightGBM is another area that we're looking to focus on. So it's not only deep learning, classical machine learning is something we're interested in as well. So LightGBM, it's really nice because of the wide variety of problems that it can solve, right? So when it comes to classical machine learning. So some of the plans that we have for LightGBM are to upgrade the version. And one of the areas that also interests us, similar to how Onyx enables interoperability for deep learning, is the fact that LightGBM also allows you to perform similar types of interoperability through its native sort of LightGBM model format, right? So what that means is you can start training ml.net, you can start training Python, wherever it is, you can go back and forth between them because of this sort of native LightGBM format. Data frame, we've heard your feedback. We appreciate everything that you provided us with. Currently, one of the focuses for the data frame for us is going to be to continue to improve that interoperability with the iDataView, so you can go back and forth, from your sort of data pre-processing workflows straight into training workflows, and then downstream you can also visualize the results of those predictions and the training process inside of a data frame. Right? And part of the improvements that come with the data frame or that are going to come is just improving the stability of it. Right? We understand that there's some work that needs to be done in those areas, so we want to continue to sort of make those improvements to make it more stable. We also want to make improvements to AutoML and tooling, so continue to improve the experience of AutoML based on your feedback. And as we introduce features into AutoML, make those available in the tooling as well. And then more importantly, none of this would matter if you folks can't be successful in actually solving real world problems with these solutions that we're providing, right? So documentation and samples are something that's really important to us. So with that, I want to say thank you. Thank you to the team who spent so much time working on delivering these features to you folks. Thank you to our partners who enable new scenarios for you folks, right? Like the text classification, sentence similarity type of functionality. And thank you to our users and the folks tuning in, because at the end of the day, right, it's your feedback that drives a lot of these decisions. So Yeah, you can find any resources, samples, code, whatever it is at aka.ms, the aka link that I provided here. And yeah, I'll take any questions.
Wow, that was awesome. We're kind of short on time. Let me see. Looking at there are a few here. This was somebody used an earlier version of ML.NET with image with object recognition, but they said it was unusable in a live video feed. And so is wondering about performance, and is that like a scenario you would expect to work?
Yeah, so that's part of what I mentioned in our sort of what's next, right? We want to focus on that performance. We're introducing new deep learning scenarios, and we realize that performance is key there. So performance is a focus for us going forward.
Awesome. Let me see. There was one question about GPU support, and I think I had read that CUDA is required, right?
Correct. Yes. So currently we only support CUDA, but kind of going along with that performance story, right? Using some of those accelerators and packages provided by the hardware vendors may enable some of these wider hardware support, right? So that's also part of our going next, but not in this version of ML.NET.
Okay, awesome. Well, we're right at time, and we got behind earlier today, so I want to keep us on time. So I'll say thanks a lot, and we'll move on to our next presentation. So thank you, Luis.
Take care.